Hello everyone, and welcome back to CS 11737 Multilingual NLP. This time I'm going to be talking about models for machine translation or other sequence modeling tasks. So first, before I go into this, I'd like to review very quickly language models. So language models are basically generative models of text, where we have a probability distribution over text, P of x, and from it we can generate a sentence or document S. So let's say we trained up a language model on a whole bunch of English text from the Harry Potter books, and once we do this, we can generate kind of a pseudo Harry Potter book that looks a little bit like this. Not the best, but maybe kind of amusing. However, perhaps some more useful class of models that we could be considering is conditioned language models. And conditioned language models don't just generate text, but they generate text according to some specification, where the input x and the output y are modeled in a probabilistic model of p of y given x. So for example, we could have the input x be structured data, like data from a database or something like this. The output y be a natural language description. Input x be English, output y be Japanese. An input be a document, output be a short description of that document. Input be an utterance, output be a response. Input be image, output be text. Input be speech, output be a transcript. And these all correspond, of course, to common tasks in natural language processing, including natural language generation or data to text generation, translation, summarization, response generation, image captioning, and speech recognition. Within these various tasks, you also hear about sequence models or sequence tasks, and these are basically tasks where you take in a sequence, such as a text sequence or a speech sequence, and output another sequence, which is very often text. So now that we have a kind of high-level idea of the class of tasks that we're thinking about, I'd like to talk a little bit about formulation and modeling. So if you remember from language models, when we discussed them before, we're basically using these language models to calculate the probability of a sentence. So the way we do so is by basically conditioning on the previous context and predicting the next word here. And by taking the product of these next word probabilities, we get the probability of the sentence itself. Conditioned language models, on the other hand, we have our output y, and we want to calculate the probability of output y given input x. And what we do is we essentially do a similar thing to what we were doing in language models, but we condition not only on the previously generated words, but also additional context here. And this additional context could be any of the inputs that I talked about on the previous slide. So one type of language model that we discussed was essentially a recurrent neural network language model. And the recurrent neural network language model, what it does is it feeds in a token, calculates a representation for the token, predicts the next word, feeds in the word that we just predicted, calculates the representation for the next token, and then predicts the next word. So this is relatively simple but powerful formulation. And what we can do is very simply essentially turn this into a conditional language model. And the way the conditional language model works is, in addition to the sentence that we want to predict, we also have some sort of conditioning context. So this is an example where a conditioning context is Japanese. So we feed in the Japanese sentence one word at a time, kono eiga ga kirai. And then based on this, we calculate the probability of the next word in the English sentence, and then feed that in one by one. And we just run this in a one big conditional language model. So one way we could treat this is we could treat this as essentially a language modeling problem, where we have certain tokens that we don't want to calculate the probability of. In other words, these Japanese tokens here. And then we do have tokens that we want to calculate the the probability of, which would be the English tokens here. Or another way we could do this is we could have different models for the input and the output. So in this case, these are called encoder-decoder models, where we have an encoder that encodes the input and a decoder that basically calculates the probability of the output. So this is a really, really simple example. This is where we have, one recurrent neural network, or maybe one encoder recurrent neural network and one decoder neural network to calculate the probability of the output. And this, can be used. It can be, relatively powerful and demonstrated non-trivial accuracies for basically problems as difficult as translation. So when we do this, we have an encoder and we have a decoder, and we would like to pass information from the encoder to the decoder. And how could we do so? One way we could do so is basically initialize the parameters of the decoder with the encoder the encoder hidden states. Initialize the decoder hidden states with those of the encoders. So this is essentially just one big recurrent neural network. We could have some sort of transform where we transform between the encoder states and the decoder states. Or we could input at every time step. So essentially we run the encoder, we calculate a representation for the input sentence, and then at every time step in the decoder, we feed in this encoded representation. So any of these is kind of a reasonable idea. If we compare these different methods, what we're doing here is we're basically asking the model to remember all of the information in the encoded state, pass it on to the decoder, and then allow the decoder to kind of decide when it should be translating or outputting whatever words it should be using next. And at the same time, manipulating the representation in an appropriate way so that it still remembers all of the content that we've seen before. If we look here, we have the encoder, we get the encoded representation to represent all of the content, and we essentially have the decoder, which then decides which word to output next based on all of the content in the input sentence. So this is going to be important when we move on later to attention. So keep that in your mind. But before we move on to the concept of attention, which is a very important concept in these sequence models, I'm going to talk a little bit very briefly about different ways we can use these models to actually generate outputs. So what I talked about before was essentially we have a model of the probability of the output given the input. So what we can do with this is if we have an input pair and an output pair, we can measure this conditional probability. But what we actually want to do in most cases is generate an output given the input. So how do we do so? There's essentially two methods to do so. One way is to do sampling, where we try to generate a random sentence according to the probability distribution. And the other way is the argmax. So in other words, try to generate the sentence with the highest probability. So first I'm going to talk a little bit about sampling from the probability distribution induced by the model. And we have a very good and simple way to do this, which is called ancestral sampling. And what ancestral sampling does essentially is it randomly generates words one by one. So we have essentially a while loop. So while we haven't generated the end of sentence symbol, we randomly sample a next word conditioned on the encoder's context in all of the previous words we've generated so far. So this is an exact method for sampling from the conditional probability P of y given x. Please ignore the typo on the slide. And there's no further work needed. And what we can see here is basically what this will do is this will sample something from the probability distribution. However, when we want to actually do machine translation or some other thing like this, it's very common that we'll want to have a single output to give to the user. And in this case, we might want to find the output that the model thinks is most likely. And one way to do this, or one way to approximate this anyway, is greedy search. And the way this works is very simple, similar to what we did for sampling. And what we do is one by one, we pick the single highest probability word at any time step. So basically, we have the same while loop that we had before, but instead of sampling according to the probability distribution, we just pick the highest scoring word at any point. This, however, in contrast to ancestral sampling, is not an exact algorithm for choosing the highest scoring example. So it has some very real problems. One problem, for example, is if we know that we would like to generate particular words in an output, like let's say we want to generate a proper name for an organization or something like this. This can be a hard problem, so the model might not be very sure about how to translate an organization's name or something like this, or a person's name. So because of this, it will have several options, and each of them will have relatively low probability. And then on the other hand, it might have, an easier word, like let's say the word to, which, it definitely knows how to translate the word to. And even if the word to shouldn't be appearing at that particular point in the sentence, it might still nonetheless get a higher probability than any of the potential options that we would have for this difficult word that may have many different options. Another issue is that it will prefer multiple common words to one rare word. So like, let's say we have an example being something like, that is to say. And the other alternative translation would be something like, in other words, or like however, or something like this. So in this case, that is to say has many common words, and each one of them may be favored because each individual choice that you have there will have high probability, despite the fact that it's a much longer sequence than some of the other alternatives. So this is just a brief outline of why greedy search may not work. It might, kind of fall into a local optimum of picking a particular next word. And because of this, as an alternative for generation, it's common to use something called beam search, where instead of picking one high probability word, we maintain several paths over the different words that we could be generating. So this is an example of beam search where we have a vocabulary of just A and B and the end of sentence symbol. And so at the very beginning, A and B have the highest probability, higher than the end of sentence symbol. So we maintain these two paths and throw out all of the paths or the path that has the end of sentence symbol. Then the second time step, we would expand all of our possibilities and maintain AB and BB, which have the highest probability, et cetera, et cetera. And so this is kind of an expansion of greedy search, where greedy search is equivalent to beam search, where the size of the number of hypotheses we maintain at any time step is exactly 1. So then the question becomes, which of these methods should you use for generating? So sampling is an unbiased method for selecting outputs from the probability distribution of the model. So this would be a good method to use when you want to essentially inspect what the model thinks are plausible outputs. So you could generate 50 examples, and those 50 examples, you could look at them and say, oh, this is kind of what the model thinks about this particular context or something like this. What things should be generated next given this context? So I think that's interesting. It's questionable at what point you should use that in some applications, like, for example, dialogue or machine translation or other things where you really are only going to be showing one output to a particular user. So now I would like to move on to my next topic, which is attention. And attention, as I said before, is a really important topic in kind of just about any sequence model nowadays. So before going into the details of attention, I'd like to talk a little bit about how we may represent a sentence. And there's a famous quote by Ray Mooney, professor at University of Texas. And who's an expert on semantics. And basically what he said was you can't cram the meaning of a whole bleeping sentence into a single bleeping vector. This was from a workshop on representation learning for NLP, but to unpack this statement a little bit, essentially, if we have a sentence, this is an example, and we try to compress all of its meaning into a single vector, if this vector isn't large enough, it's going to be very hard for us to essentially express all of the different sentences that we could have in the world within this single vector space. And this is a 4-word example, so it's relatively simple compared to many other examples where we could have, for example, 80 words in a particular sentence, or even thousands and thousands of words in a document that we've seen so far. So what attention does instead is basically, instead of trying to compress down all of the information at any one point into a single vector, what we do is we allow every single token or word in the input to have its own vector, and then we allow the model to reference the appropriate parts of the sentence when it needs to make a decision. So I'd like to give an analogy for this, which is when I worked as a translator, if you asked me to read a whole document and say, read this document, and then you take away that document from me, you like turn off my computer screen, or you take away the paper that you gave me, and then ask me to translate it, that would be extremely hard. I just don't have the memory capacity to do so. However, if you allowed me to read the document, then you allowed me to translate while going back and referencing each of the individual words in the document. That would be much easier for me to do. So that's essentially what attention does, and we'll go into the technical details next. So what we do with attention is we encode each word in the sentence or input into a vector, and when decoding, we perform a linear combination of these vectors weighted by attention weights, and use this combination in making our next decision or picking the next word. So what this looks like in a conceptual diagram is essentially, let's say we're doing Japanese to English translation. We have all of these inputs here, each corresponding to one vector. And we've already generated the words I and hate, and would like to generate the next word in the sentence. So we have one vector for each of the inputs, and we also have a vector representing our decoder state. And we use a query vector corresponding to this decoder state, and key vectors corresponding to all encoder states. And for each query key pair, we calculate a weight. So we use essentially an attention function represented by this gray gear, and we apply this for each pair of query and key vectors. So this gives us weights that can be, arbitrary real numbers. And then we take these weights and we run them through a softmax and get a vector over all of the input that is essentially kind of looks like a probability distribution. It has all these values here, and each of the values is between 0 and 1 and adds up to 1. And what this attention vector is essentially telling us now is it's telling us that we're focusing kind of 76% of our focus on the first word, 8% of our focus on the second word, 13% of the focus on the third word. And this is good because, if we want to generate the next word corresponding to this first word in the Japanese or input sentence, then this will allow us to focus more on the input. So what exactly do I mean by focus? So this is kind of abstract. So what does it mean mathematically? What we do is we combine together value vectors. Usually they're these encoder states like key vectors, and we take the weighted sum. So we multiply each of these vectors by the attention weights, attention scores, and we combine them together into a single vector. So now we've taken our long sentence and combined it into a single vector, and we use this in any part of our model. So we might feed this into our current decoder in order to help it make a decision over the next word. Now, the important thing here is we're not taking completely independent of context all of the inputs in the input sentence and collapsing it into a single vector. Rather, it's context dependent, which means that at every time step, we can use which parts of the input sentence that we would like to make our final decision. So a graphical example of what this looks like for French-English translation here is you can see essentially that we're generating maybe French words. And when we do so, we essentially get a vector where a lighter value corresponds to a higher attention probability on the input. And you can see essentially that when you're generating the word le, you focus on the, and as you step through, you can see that each time you're generating the word, you're essentially focusing on the corresponding word in English. So I talked about the little gray gear a second ago, and this gray gear corresponds to an attention score function that takes in a query Q and a key K. And there's a bunch of different ways we could formulate this. We could formulate it as a multi-layer perceptron, where essentially we take the query and key, we do a linear transform over the concatenation of the two, we extract features using a nonlinearity such as tan h, and then we have another vector that is multiplied by these features to get our final score. So this is a flexible method that's often very good with large data because, you know, this kind of feature extraction method can calculate any function we want because neural networks can calculate any function we want. So this works well with large data, but when you're using smaller data, there are often some better approaches. So one example is the bilinear function, where we take the key and the query and we put a matrix multiplication in between them. So essentially we are doing a linear transform of the key and then comparing it with the query. And in the extreme version of this bilinear function, we have the dot product method, where essentially that center weight matrix is an identity matrix. So we make no change to key, and then we just take the dot product with the query vector. So this is extremely simple. It has no parameters, but it requires the size of the two vectors to be the same, because essentially the query and the key have to be the same size in order for us to take the dot product. And finally, there's scaled dot product attention. And essentially, the problem with the dot product is that the scale of the dot product increases as the dimension of these vectors gets larger. And the way we can fix this is essentially scaling by the size of the vectors. So we take the query and the key, we take their dot product, but we also divide this by the square root of the size of the key vector or the query vector. And this essentially allows us to control for the fact that the variance between these values gets larger as the size of the vectors gets larger. So attention is great. It's a very, very important piece of most models we use nowadays in NLP. However, one thing that we should be careful is that attention does not actually correspond to an alignment between the words in the sentences. And to give an example here, this is an example from Koehn and Knowles, 2017. They demonstrate how you can train actually a quite competitive German-English translation model where it gets all of the attention values off by 1. So essentially it's looking to the right every time. In addition, you can actually show that you can manipulate attention so that it intentionally doesn't focus on any of the actual aligned words, and you can still do very, very well. So I think the appropriate way to think of attention is more that this is a tool that makes it easier to encode lots of information in the input, and less as a tool for, interpreting the outputs, etc. Or interpreting, like what the model was focusing on when it makes a particular choice within the model. Okay, so these are the basics for attention, and there have been a number of improvements to attention since it was introduced several years ago. And the first one, which is a feature in several models, including at one point the Google Neural Machine Translation model, is consideration of coverage. So one issue with machine translation models, essentially, or neural machine translation models, is they can tend to drop or repeat content. So you might see that it drops a whole part of the sentence, or it repeats the same word over and over again. So what coverage does is essentially we model how many times words have been covered. So a couple ways we can do this is by imposing a penalty if attention is not approximately 1 over each word. And this is kind of saying, like for every word we expect that you're going to focus on that word 1 time. And there's in some way a word-by-word translation between the input and the output. Another way you could do this is adding embeddings to the input to indicate the coverage of those words so far. So essentially adding embeddings that indicate that attention has appeared on a particular word so many times. So another important development that is used very widely nowadays is multi-headed attention. And multi-headed attention also kind of goes back to the idea of attention is not alignment, and rather attention is a way to pull in various types of information that are important to make a decision at any time step. And the idea is that instead of having a single attention vector, we have multiple attention heads that focus on different parts of the sentence and pull in different varieties of information at any time step. So to give a very salient example that's very easy to understand the benefit of this, we have a model for essentially summarization where that model is equipped with the ability to copy words directly from the input. And this is really important if you want to summarize things. In this case, it's summarizing source code, but it could be anything else. Because when you summarize, you still want to be faithful to the input content, so you want to have the ability to copy salient parts of this. So what this model proposed was essentially 2 attention probability vectors, so alpha and kappa here, where the alpha vector is for regular attention and the kappa vector is for copying from the input. So what you can see is essentially the alpha vector kind of pulls in information from all over the input, whereas the kappa vector focuses very, very sharply on individual tokens that you would want to copy. So this is a model that essentially has 2 attention heads. It has one attention vector that focuses kind of just on general information that's useful, and another vector that focuses specifically on words that you would like to copy. Now, this particular idea has been used in a more abstract way. In the way it works, essentially, is instead of having different attention heads that actually have very different kind of behavior within the model, you just kind of arbitrarily choose a certain number of attention heads, 8 attention heads, and allow them to each calculate their vectors independently. And then you can hope the model learns to use these different attention heads in different ways. So one example here is we have the word making, and when we calculate the essentially representation for the word making, we take in one attention head that basically looks at the word itself, another attention head in pink that is looking at the previous word, which is kind of important information a lot of the time. And then we have other attention heads that are focusing, for example, on the object of this verb making. So it's looking on more difficult. And this is important for something like translation, because in order to do translation, you of course need to know the identity of the word that you're translating, but you also, for a kind of ambiguous verb like making, you'll also need to know what you are making. So if you're making a cookie, the translation will very likely be different than making something more difficult. So that's kind of the power of multi-head attention. It allows you to pull in various types of information here. So another thing you can do is supervised training, and this also has been used in production translation systems, for example. And the way it works is sometimes you can get gold standard alignments a priori, and the way you can do this is for example, by asking humans to align the words in the input and output sentences for translation. So another way you could do this is you could pre-train with a very strong alignment model, maybe using a translation dictionary or something like this, and you could get alignments that maybe aren't as good as manual alignments, but still pretty good. And what you can then do is you can then train the model to match these strong alignments. So what do you get from this? You get a couple things. Number one, you could perhaps bootstrap the machine translation model to make it learn a little bit faster, already knowing which words it should be aligning between the source and target. But perhaps more importantly, this can give you a larger level of trust in your interpretation of the inputs and outputs. So, if the model has been trained to match manual alignments, then this can, help ensure that at least for some of the time it should be matching human intuition about what words should be aligned. Okay, now I'd like to move on to the next part, which is very important for modern machine translation or other sequence models. So I'm going to talk about self-attention and transformers. So self-attention, basically the idea behind self-attention is that each element in the sentence attends to other elements in the same sentence. And so the way this works, to give an example, is we want to calculate the encoding for the word this. And what we do is we take the linear combination of the value vectors between all of the words in the sentence. So maybe for the word this, we would like to know, the word itself, of course, but we might also want to know which verb it is the subject of, for example. So we would pull in, 80% of our information from the word this itself, and 20% of the information from the word its. Then if we wanted to translate the word is, we'd also want to know maybe the subject and the object of the verb, like I mentioned before. So we pull in information from the subject and object of the verb. Similarly, for a pronoun, maybe we need to know, for a determiner. So maybe we need to know the noun that this corresponds to in order to know whether this should be translated into a masculine or feminine determiner in the language that we're translating into, if it's a language like French or Italian that marks the gender of determiners. And finally, we do that for example. So notably, this is essentially yet another sequence model. So it's like an RNN, it's like a CNN, where basically we could take in a sequence and we can calculate vectors for this sequence. So why would we want to use self-attention over other sequence models? So one really, really big advantage is that unlike recurrent neural networks, where recurrent neural networks, every time we calculate the probability of the next word in a sequence, we need to have already calculated the representation of the next word in the sequence, we need to have already calculated the representation of the previous word. The self-attention is parallelizable. So we can essentially calculate the representation or calculate an entire layer of self-attention in parallel. And this allows for fast training and even fast calculation on GPUs. Unlike other things like CNNs, which kind of focus on local context most of the time anyway, they make it very easy to capture global context. So for example, if we wanted to take a verb like making and pull in, the object of that verb, it's not that hard to do so. We can look all the way to the end of the sentence, grab the object of the verb, and update the representation of the verb in a single pass. Also, empirically, the results have tended to be good, and this is a widely cited reason for why people use self-attention nowadays. I would like to point out that maybe this isn't the most convincing reason to use self-attention. There have been some reports that essentially demonstrate that RNN-based models are pretty competitive as well, all things considered. I'd say actually probably the major reason why people use self-attention is perhaps the first and second reasons. It's just a fast, very efficient way to capture global context, which makes it very conducive to training over, many different large data sets. One downside, however, is if you want to consider very long sequences, the calculation between the key and query vectors is quadratic in the length of the sequence. So it isn't trivial to run this over, for example, a 1,000 token document or 10,000 token document without some sort of tricks. So this idea of self-attention has come to be sort of synonymous with a specific model architecture that uses self-attention called the transformer. So you don't necessarily need these to be synonymous, but this combination of various elements is proven very useful. And to summarize what the transformer is it's basically a sequence-sequence model based entirely on attention that has demonstrated strong results on the WMT translation tasks and other methods. Other tasks. And the way it works essentially is we take our input embeddings, we add something called a positional encoding, which I'll talk about in a second. We run it through some layers of multi-headed attention, addition and weight normalization, a feed-forward network, and addition and weight normalization here. And we do this over and over and over again, so maybe 6 times, 8 times, 12 times. And then we also have a decoder that basically takes the output embeddings, it does self-attention, and then it does attention over the input. So this is kind of like what I was talking about before. We do attention over the input, then it has a feed-forward layer. So this is kind of the shape of the transformer encoder and the transformer decoder. So we're going to have a discussion about this in more detail in class and go into kind of the details. I'd like to point out basically that essentially the transformer has a whole bunch of tricks that go into training it. And it's important to know that these tricks are there and they're kind of important or necessary for training these models effectively. So the tricks essentially are that number one is its sequence model, it uses self-attention. Each layer combines words with others, both in the encoder and in the self-attention block in the decoder. It also uses multi-headed attention. So in the original transformer paper, it used 8 attention heads, each learned independently. It's using normalized dot product attention. So essentially it's using dot product, or maybe you could call it bilinear attention also, because before it takes the dot product, it multiplies it by a transformation matrix. But either way, it's using this sort of attention with the normalization to prevent large vectors from getting their scale too large. And it's also using positional encodings. And these positional encodings, basically what they do is if we use self-attention without any concept of which position the words were in, if we had an identical word within the same sequence, like let's say we had the word the twice, we would have no way of being able to distinguish between them. So what these positional encodings do here is we add a different encoding for the first position in the sentence, the second position in the sentence, the third position in the sentence. And what this allows us to do essentially is, number one, consider word order. So consider, like words that are next to each other should probably be more likely to be focusing on each other. And also distinguish between 2 words with identical surface forms that appear in different parts in the sentence. So like a the in the 3rd position can be distinguished between a the in the 10th position. In addition, there are a large number of training tricks. So these training tricks have included layer normalization, which essentially normalizes the values of the hidden layers to make sure that they have zero mean and unit variance. And what this does is this helps ensure that the layers remain within a reasonable range and we don't have like exploding values or rapidly diminishing values as we go through the layers of the network. We also have a specialized training schedule. So this essentially adjusts the default learning rate of the optimizer, the atom optimizer that it uses, by gradually increasing it and gradually decreasing it. It uses label smoothing. Label smoothing inserts some uncertainty into the training process to try to essentially prevent the model from overfitting too much to the data that we have. And it also uses masking for efficient training. So just to go into the very last one, masking for efficient training, essentially what we want to do is we want to perform training in as few operations as possible using big matrix multiplications. So like I mentioned before, this is a major benefit of using the transformer. And the way this works is we can do so by masking the results for a particular output. So essentially, when we calculate the representation that will be used in predicting the word I, we only use these 4 vectors here, and we mask out all of the other ones so that they can't be referred to. And then when we predict the word hate, we also consider the previous value. When we predict the word this, we consider the previous 2 values, etc., all the way to the end. And so if you do some computational tricks, this allows you to actually do the training very efficiently. So now I've gone through essentially the transformer self-attention and given some basic ideas. As I said, we're going to discuss this more in class to go through some of the details and discuss more. But before we get to the discussion, I'd like to talk about a unified view of sequence models. So taking a step back, if we remember what we did before, we did sequence labeling. And in this case, we kind of had a unified view of this, which was like we take in an input, we run it through a feature extractor, we get a single representation for each word in the input, and then we make a prediction one by one over the outputs. So we can also think of sequence modeling in a similar way, where we have I like peaches, the input, we run it through a feature extractor, we get vectors for each word in the input, and then on the output, we have a masked feature extractor, which basically can extract features referring to every single input except the inputs that are in the future. And this is called, masked attention. It's also called causal attention. I won't go into the details there. And once we do this masked feature extraction, we can then predict all of the words in the output. So I think the reason why this unified view of sequence models is good is essentially it allows us to think about the transformer as one variety of feature extractor and masked feature extractor. But we could also think of an RNN in a similar way. An RNN or a bidirectional RNN is a feature extractor. A unidirectional RNN can also be viewed as a masked feature extractor because it can't refer to things in the future. So that kind of gives you the flexibility to think about these models in a way that makes them very easy to conceptualize and extend. Okay, so what we're going to do in class, it's not actually an assignment, it's just going to be informative, hopefully. And what we're going to do is we're going to have a code walk. There will be no graded discussion, but we'll go through this annotated transformer website. And we'll go into more depth about the transformer model and discuss some of the design decisions, their motivation, discuss some of the alternatives that you could be using at any of the points to these design decisions. So that is all I have for today. So thank you very much for listening.